this is definitely a departure from my usual content. I am not going to talk about PagerDuty today. I'm happy to talk PagerDuty, incident management, post-incident reviews, blamelessness, all that stuff in the open spaces, or catch me at lunch if you want to do that. What I'm going to talk about today is some stuff I was curious about. In my copious free time, I'm working on a graduate certificate in AI, and this was one of my classes. I'm doing this because I have a master's degree in computer science that predates all of this stuff, which makes me feel incredibly old. So in a chance to recapture my misspent youth, I've been taking some classes. If you have any questions about anything, if you want to get in touch with me about stuff, PagerDuty, whatever else, I'm very much available online. I'm no longer on Twitter, but I am on Blue Sky with the same handle, so reach out. So, who's not using AI? Right? Yeah, not even a lucky few, right? AI has been interesting. We'll maybe have some thoughts and chat on that later. But one of the things that is also super interesting is these sort of horror stories that pop up. People asking sort of general models to do very specific work with very specific data. And it fails spectacularly. It's not meant to do that. Cory Doctorow refers to these machines as word-guessing machines. He's almost right. They're number-guessing machines, and then they translate those numbers back into words. But under the hood, we are very much guessing and doing strange things with them. And sometimes that's okay. Gmail was one of the earliest applications to sort of incorporate some of these AI models into what they're feeding to you as they're trying to help you write an email, because you all evidently need help writing email. And the original training corpus there was the Enron emails. Who's old enough to remember Enron, right? Good. So sometimes that's fine, right? We have seen no additional increase in securities fraud since Gmail learned how to write email from Enron, so maybe that's all fine, right? It could be fine. In other places, it's not so fine. And what we're seeing is that people are trying to shoehorn things into the wrong kinds of models, when under the hood, these things aren't really that difficult to approach if you kind of have a place to get started from. So that's kind of where I've been playing around, and where I was hoping maybe it would help some of you if you are interested in playing around as well. So I will apologize in advance. There will be some math. I know it's still taught because my niece called me about some homework that she was working on with points and lines and all of that kind of stuff. Who recognizes this greatest hits of middle school math? Yes, y equals mx plus b. Now, the reason we bring this up is because the AI models we're working with today, the original research with these was started in the 1960s. Alan Turing wanted to teach machines to think like humans in the 1950s. And we're like, we've got a bunch of human brains. Why don't we invent something else? But that's where we got to. So starting in the late 1960s and up through the early 1980s is where a lot of the foundational research was done. And the reason it feels so scatterbrained and very, very fast now is because we've only just now gotten to the point where you can apply this kind of stuff with enough data and enough hardware. I mentioned I finished my master's degree in 2007, and nobody in the room besides me had access to enough hardware to even think about doing anything with these kinds of models, as it's too expensive. I worked at AOL, would never been allowed to, but at least I had access to several thousand machines had I wanted to. So under the hood, what we're after is predicting an outcome based on some inputs. My X is my input. I find the variables for M and B, and I eventually get to Y. And I need some place to train that with. Now, when we think about what human beings can think about, 2 dimensions, very easy to reason with. That's a slab of paper, we draw the graphs, my niece calls me for help, the whole 9 yards. Where we get to then with that, we can make basic predictions off of very simple data. And for some use cases, this is totally fine. It gets you close enough to what you're after. Other places, data is weird, right? The big problem is data is dirty. And in a lot of places, your data is garbage because it's entered by human beings, and there's transcription problems, and there's misunderstandings, and there's people just being lazy. If you've ever tried to get data out of a CRM database and you're like, why don't my salespeople put any of this data in here? And you're like, you're not alone, because they never do it. So if you're trying to work off of that, you don't have full data. So we're looking for, just at the basics, linear regression is looking for relationships in data. And it's fairly easy for us to understand with small data sets. And you can do this in a spreadsheet. You can do it in Excel. You can do it in Google Sheets without any extra packages. It doesn't need anything special. It's very easy for humans to then think about. So the data I'm going to be working with today, we're going to look at some code. I'm working with some test data because I know it's right, because I know it's complete. And it's very basic data. It's from the Singapore housing market. It's a very standard academic data set, has 25,000 rows, so it's not huge, 11 columns. And we're going to be working with numerical data, so I don't need any GPUs, and I'll talk about that in a minute. But this is where we're getting started. If I wanted to know the price of a property based on some characteristics, how much of a model, what kind of model can I build to do that? And if you have data of your own, I work at a SaaS, right? So we want a model of, if you're using these features, how long can we think you're going to stay with us? If you're not using these features, are you more likely to churn? Like that kind of data that comes up in our regular work. How many hits relate to shopping cart conversions and all of those kinds of things. But also it's like basic stuff, right? Like the temperature outside, how many ice cream cones can I sell if I work at an ice cream stand? Like all of those kinds of relationships and that kind of data all sort of relates to these same kind of models that are all built in the same assumptions. When we get to higher dimensions, it's harder for humans to visualize. Does anybody remember the hand thing that you had to do with X axis, Y axis, and Z axis at the top, right? And you're like, okay, it's super weird. Higher dimensions become very hard to think about because we're limited to the dimensions that we live in. Modern data sets have hundreds and maybe thousands of dimensions. And we think about the general application models, they might have millions to billions of dimensions that they're working across. We're not going to get to that. We're going to stay in the shallow end. And that's the pun of the name of the talk. Where these things then relate is what we're building off of them is neural networks. And this is another thing that sort of harkens back to the early researchers wanting to teach machines to think like humans. So they called it a neural network. And it looks like regression on steroids because it's kind of what it is. We have the Y that we want to try and predict, and then we have some X's that contribute to it, and some other variables that we're going to find in a sort of discovery process. And for those of us who like things to be sort of spelled out or a little bit more predictable, the weird thing about some of the way these things get built is that it ends up being very empirical. And when we're working with our own data, there's some experimentation that comes in to figure out what fits best and how we're going to find these values for things like W and B. And these are your weights and your biases, which you may have heard terms when people are trying to sell you a model. It has weights, or it's open weight, or it has these biases. I think somebody named their company that, expecting everyone to understand what they're talking about. So neural network, has anybody seen this kind of picture before? Okay, awesome. So our neural networks, the most basic components, have three different kinds of layers. The first layer is my input layer, which is what I tell the machine, this is what I'm giving you. This is the data that's coming in that you need to work with. Then I have these hidden layers, and I can have one or more of these, and they can do all kinds of convoluted, bizarre things. The most basic ones have some nodes in them that are going to do some math, and then eventually we're going to get to the output layer, and that defines what the output that I want. I'm doing something very basic here. I have a couple of input X's, and I have one output in my Y's. You may have data that has multiple kinds of Y. You have categorical data, and there are absolutely ways to put those together. The hard thinking part for folks is this is all probability based, right? Like when I get to Y, how close am I? How probable is my Y to being correct? And when I get closer, it's because I have changed all of those other little dials in the machine. In my mind, neural networks look more like a Rube Goldberg machine. And I have changed the way the path flows through them a little bit as I work through all of the layers. And it gives us dials and places to change things around to get closer to the Y that I want. I want closer to the output that I'm expecting. So they're very experimental in that way, especially when you're working with your own data. So I'm going to look through some tools here. I'm going to flip to do some code. The tools that I'm working in a Jupyter notebook. People have feelings about Jupyter, but it works for this kind of thing. Also Anaconda, I am not natively a Python programmer, so doing environment management in Python is not something I enjoy, but I'm using Anaconda here. I'm not using GPUs, but if you would, you could use Colab, which is a Google product, which is very interesting. We'll talk about in a minute. I'm also using Pandas and NumPy for math and Matplotlib for graphs. I'm not going to go through all of the regression tools, but I'm listing them here in case you're interested in them. And then the neural network stuff that I'm working with is TensorFlow and Keras. There's another entire workflow setup and another tool chain based on PyTorch, which, if you've heard of PyTorch, yeah, a few hands. So that's another option for these kinds of experiments. Where you can find data sets and pre-built models, there's a whole bunch of things that have sort of sprouted up across the internet over the past couple of years. Hugging Face is probably the most well-known. Also, I find the most hard to trust what you're getting out of it. The data sets tend to be very messy or make no sense, right? I want a data set, I want to make predictions off of it. I need it to make sense. But if it's a created data set and I get negative values for something like how many points does this person have in their account? Why do they have negative points in their account? That doesn't make any sense. Anyway, I can rant about that forever. Universities and governments also have a bunch of stuff that have posted. I live in New Jersey. The state of New Jersey has a gigantic data website that has all kinds of interesting things on it from our government. So lots of places to find things if you happen to be interested in playing around and experimenting with stuff. Okay, so let's do some code. So like I said, I'm in a Jupyter notebook. This is in my GitHub, so if you're really curious about it and you want to work through it later, feel free to download it there. But there is a lot of discussion in it, and I'm just going to start clicking through some things so you kind of get an idea of how it runs. I've already loaded up the slow parts, like importing all of my libraries and my data. The interesting thing, if you need nothing else, the one package that's here that I find the most helpful is called Pandas. Does anybody work with Pandas? Awesome. So Pandas is like a spreadsheet built for engineers. Like it brings things into what's called a data frame rather than just a straight two-dimensional environment. So you can do a lot of parsing and manipulating and modifying of the data in very interesting ways. So it's super helpful from that. If you're super interested in Pandas, everybody and their brother who has like a YouTube channel probably has a video on how to use Pandas. And they're all super fine. So we can start looking at data and figuring out what's going on. One of the big problems when we start looking at data is that it doesn't always make any sense, right? There's going to be garbage in it, number one, but Pandas can't make any assumptions on what the data looks like for some of the things that you're going to give it. And one of the things that's super interesting is that it will just default to an object type instead of saying, oh yeah, this column is obviously numbers. It's a kind of a signal to say, okay, somewhere in here, somebody has put like NaN for not a number or some other thing, and Pandas can't make an assumption about what the numbers are. But we have to turn everything into numbers to be able to use the models. That under the hood here, we cannot deal with incorrect data of that type, which means if you are cleaning data, like you end up tearing out a lot of stuff there, which is another whole discussion. But we can kind of get an idea of what the data looks like. Like I mentioned before, it's 25,000 rows, 11 columns, so not huge. And it's a mix of numerical and text data about properties in Singapore, okay? And we can do some graphs, right? We can see, okay, here's some prices for the value of this particular properties based on the floor area. And it looks like I've got an outlier, and I can clean that up with some tooling, because when we're moving our dials in that neural network, outliers tend to have an oversized effect, and they can skew our model away from what we want it to be. So we can pull those out. And then we can start looking at, okay, well, if I wanted to be able to predict the value of these properties based on the data that I have, I can start with a correlation matrix and start digging around to see how well related they are. And that kind of helps us sort of pinpoint, if I'm looking at my personal data or my data from whatever project I'm working on at work, I can say, okay, so there's some relationships here. There's some things that maybe aren't really compounding, but they are maybe helpful, and we can start with that. And then we'll go through the linear regression part. That's the part that we've already talked about. I've got X and Y. I'm looking for the line that goes straight through them. So let's take a look at what it looks like for the neural network. So I've got my data frame here, and what I want to be able to do is say, okay, well, here's the value. Maybe this is my 2025 data. I want to be able to predict property values through 2026 based on some similar model, right? I'm going to get close, right? So I'm going to look at the basic things here because I don't want to talk about doing text conversion. But when we do have a lot of numerical data, whether it's hits to your service or customer engagements or any of those kinds of things, a lot of that does come in as numerical data. What we need to do, though, is trim it down to the same order of magnitude, right? When I'm looking at my data here, the value of these properties is in the hundreds of thousands of Singaporean dollars. That's a very large number. When I'm looking at floor area, it's around 1,000, whatever these are, right? Square meters, probably square feet. So that's a medium-sized sort of number. And then I've got bedrooms and bathrooms, which are very small integers. And as my model works through my neural network, when it sees certain larger numbers, they're going to be outweighted towards the model and kind of swamp out the small numbers. So I have to do some math to put them all sort of in the same range so they can actually impact the model in the same order of magnitude. So I'm going to clean some of that up here to give myself a better set of data to work with. There's a couple of different ways to do that. For large numbers, you can just divide them by multiples of 10, and that's fine. And for other things, we subtract them from the mean and divide them by the standard deviation, which is another empirical kind of thing that just sort of works. It sounds more impressive if I say it in the Russian accent of the professor that I had for this class. All right. So the next piece is where the probabilistic nature of these start to come in. I've got a data set. You might have the same data set. What we're going to do with it is we're going to divide it up into training data and testing data. And we're going to do this in a random way. I have 25,000 rows. I want 80% of them in my training data and 20% of them in my testing data. I'm going to use a random seed to do that. Now, if you and I use the same random state here, we can preserve some of that and get something very similar. If we use something different, and you can think about this as being like a salt when you do a password, we'll get totally different data sets for training the model. We will get different models. We will get different weights for those values in the model, right? So the weird part of this, the non-deterministic part of it, is sort of built into the very beginning of the set when I'm actually building the set that I'm going to train the system on. So we build two of these. We just split the data that we have, and I'm going to use one set, X's and Y's, to train the data. And then when I get to testing, I'm going to say, okay, we're going to make some predictions. Tell me how close I get. To build the neural network itself, I'm using, as I mentioned, TensorFlow and Keras, which is a fairly simple sort of API on top of these libraries. I can build the model exactly the way I drew the picture. I have an input layer that has a shape of just two. I've got two things I'm working on right now. I have floor area and I have bedrooms. And then I'm building a sequential model, and there's other things you can do in here. If you're doing graphics, there's a whole bunch of wild stuff that it'll do. I have one middle layer. I put those 3 nodes in just like I drew the picture. You can experiment here. You can put more nodes in. You can put fewer nodes in. You can try it out, see what it does for you. And then there's an activation here, which is how the math happens for changing the weights. And there's only a handful of these that seem to work. And these are all sort of, again, found experimentally. The last layer is my 1. My 1y is what's coming out here, and that's really all I have. That builds the whole model. And the way these are assessed is how close they get to the y, and that comes in as loss. If you've heard that term when you're talking about AI models, the loss is how close I get to what I was expecting. And that's where I start to track, I compile my outputs. And we'll run it and see what it does. So this is a very small model with a small data set. What I'm telling it is, I want you to run through the entire data set 30 times to train those W's, find those values. And to do that, I have to go through the data set lots of times to see how close my predicted Y gets to what I expected. Now, this part, again, is experimental. My model might be very different from some other data set that I have that I'm going to run a similar model on. It might take a lot longer to find some answers. In this case, it comes in very quickly, and we can do a graph to see how it went. So very early in my training, it says, okay, this is as close as I'm going to get with the data that you gave me. And it's running very close to what is expected. That's great. Now, overall, we don't really know how close I'm getting to predicting anything, but I am getting close enough to what the training data is telling me. And there are other cases where these things oscillate or they swamp themselves out and they're actually not giving you good data. I'll have references for you at the end. You can think about that, those kinds of things. So what I do know now, though, from this model is because it converges so early, the next time I want to work with this, I don't need to sit and wait for it to run all 30 times, especially if I have a larger data set or a larger model, it's going to be slower. Then I can trim it down and say, okay, well, we're going to run this maybe with 15 runs through instead of 30, and that cuts down some of your training time. When you think about the large general models and how long it takes them to train, like the data set is very, very large, and the middle layers are very, very complex, and there are a lot of them. And who knows how many are actually in some of the commercial models. Some of the open source models might have hundreds of layers in the middle. They're doing interesting things. So that's all great. Now, how do we get close? Let's do some predictions. I've got my testing data. Remember, that was the chunk that I chopped off of my data set to do for testing. And I'm going to make some predictions based on the Ys that I already knew and my model and what the model tells me. So I already know the X's, I already know the Ys, and I'm going to compare them. And we'll do a scatter plot there. And we're like, meh, that's not great, right? Not super good, right? And the yellow is my predicted values. They're all kind of clustered together. So not sure this is the best combination of data columns for the prediction model that I want to make. The blue was the original data, right? That was the original Ys that were included. So we've got some, and maybe this would be enough to like base some initial assumptions on, or some work that was maybe less risky. But let's see if we can get a little bit closer. So I have other data here. We're going to try it again, same neural model, but I'm going to add more data to it. So in addition to floor area and bedrooms, I can add bathrooms. So we're still working with small numerical numbers. So we're going to do the same cleanup with the data there. And because I've picked new columns, I'm building a new training and testing set off of that. But I'm going to use the same model. Now, to get different output here, you can add, like I mentioned before, more layers. They can do different things. They might have different activation levels. There's all kinds of other stuff that you can do in here to get to the point where the model that you have predicts for the data. If you have custom data, custom model that you build is going to be sort of the best thing that you can fit on there rather than large generic models. So run it through again. So the only thing I had to change here was the input. Now I have 3 values in my X column, and that's the only thing I changed here. Everything else is the same as the last model. So let's see how close this one gets. Still converging a little bit later, maybe after the 7th run, but it didn't then just completely flatlines. And we'll see if it gets any better with its predictions. So we run some predictions off of it. And again, all of this is built into the libraries that I'm using. So it's very easy to put together there. I'm just checking out my data sets here. And then we'll do a scatter plot. And it looks even worse, right? So you don't know when you go into the data sets what it's going to give you, and the experimentation part of it becomes part of what is super important for dealing with some of these, with your own, especially with your own data. When you don't know what is related, right? You have a lot of data that we work with the systems that we run, and you don't really know right off the bat. Maybe you have some intuition about what is impacting things, but you don't necessarily know exactly what is looking there, what you're finding, and maybe how to predict it. So there's a lot of different options for these. I find them really interesting, especially because some of the enterprise tooling that we have is a per seat license, and I don't have licenses for it, but I can get hold of a CSV full of data and do some playing around and some predictions off of the things that I need to see. So I found these super interesting. I find some of the experimentation sort of infuriating, honestly, because I want things to be a little bit more sure, but that ends up being very much part of it. So some of the other interesting stuff that these libraries provide, sentiment analysis. I work in developer relations. We do a lot of work with our community and postings, and we're in charge of reading social media and all that kind of stuff. And sentiment analysis for a long time was a very, very expensive tool to buy. And there's now an open source kit that's actually very, very good at it and is specifically tuned for social media. So if that happens to be part of what your job is, if you're looking at NPS scores as a product manager or something like that, the Natural Language Toolkit has a sentiment analysis tool in it called Vader that is tuned for small snippets of data. And like social media posts and that kind of stuff is very, very good at giving you sentiment analysis across a set of posts or reviews or that kind of thing, and works in the same similar framework as what we just saw. The TensorFlow tools have a lot of other things they can also do. So you can do time series prediction, you can do image manipulation, you can do image relationships, reconstructions, all of that kind of stuff built in the same libraries with different options into the neural networks, which is, there's so much to play with and to fiddle around with. Is super interesting there. So when you're working with that stuff, as soon as you start looking at images, that's when you're going to want to look for a GPU. I'm on a 7-year-old MacBook. I do not have a GPU. I barely have a CPU in this thing anymore. So looking for places to run things if you want to do image manipulation, stuff like that. I like Google Colab. It's super easy to work with. You can select the kinds of kernels and frameworks that you want to use. You can select GPUs. You just have to pay a little bit of money there or get a subscription to that. Super easy to sit and do. There's other things you need to watch about where you store your data and that kind of thing, as you would with anything else in the cloud. But it's super interesting to play with. So some of the references for this, Deep Learning with Python is the 3rd edition is free online, and that will take you through a bunch of the stuff that I just went through. Hands-on Machine Learning with Scikit, Keras, TensorFlow is an O'Reilly book. If you still have an account for what used to be Safari for all of us olds, it is in there and super helpful that way. And now they call it like online learning or something else generic like that. If you're interested in the notebook that I just showed you, that is in my GitHub, and happy to share that with folks if that's interesting to anybody. Now the graphic that's here is your $1 million how to bore people at dinner parties. Does anybody go to dinner parties? This is stochastic gradient descent. So it sounds mathy. It's very mathy. That's what regression is when it's on shrooms. It's like trying to figure out how to get through these n-dimensional objects or data sets and find the most optimal place for how all the data relates. And this is how one renderer has decided to show it. But again, super interesting. I find it super interesting. I hope you do too. I hope that folks can find a place to sort of come back to owning your own data and owning the things that you're doing with it, rather than blindly trusting what some of the big providers are trying to get you to do with it. So with that, thank you very much.